There is a certain kind of beauty that physicists fall in love with, and it is not the beauty of color or music. It is the beauty of symmetry. Symmetry suggests that the universe is not merely a pile of facts, but a coherent structure. It suggests that nature has preferences and rules, that it repeats itself in patterned ways. Symmetry is a promise that if you understand the pattern, you can predict the behavior even before you measure it. For much of the 20th century, symmetry became one of the guiding ideals of physics. It was not only aesthetically pleasing, it was practically powerful. It allowed scientists to constrain theories, to rule out impossible behaviors, to build deep frameworks from minimal assumptions. Symmetry became a kind of moral compass inside physics, pointing toward what must be true. And then, in the middle of that century, one symmetry, long treated as sacred, failed. The person who proved it failed was Chien-Shiung Wu. Wu's story is not only about a discovery, it is about precision as a form of courage. It is about what it takes to challenge a belief so widely held that it has become invisible. And it is about the way recognition, like symmetry, can break. Not because the work is weak, but because the world is. Wu was born in 1912 in a small town near Shanghai, in a China struggling with modernization and political turbulence. Her father, a progressive educator, believed fiercely in the education of girls, and he founded a school that allowed her to learn in a society where women's education was still contested. From the beginning, Wu's path was shaped by both support and resistance, support from family, resistance from a world that did not yet imagine women as leading physicists. She studied physics in China and then moved to the United States for graduate work, eventually earning her doctorate at the University of California, Berkeley, in 1940. Berkeley was a center of nuclear physics then, charged with the energy of new discoveries. The nucleus had become a frontier. The tools of particle detection and radioactive measurement were becoming more refined. Wu entered this environment with a rare combination: deep theoretical understanding and extraordinary experimental skill. She became known early not merely as a good experimentalist, but as someone whose experiments could settle arguments. If you want to understand Wu's greatness, you have to understand what precision means in experimental physics. It is not only about careful instruments, it is about temperament. It is about patience, stubbornness, and an almost ethical refusal to accept noise as an excuse. A high-precision experiment often requires long hours of repetition, control of temperature, control of impurities, elimination of systematic error, and a level of discipline. Imagine, the great experimentalists are not merely technicians, they are architects of truth under difficult conditions. Wu became such an architect. During World War II, she worked on the Manhattan Project, contributing to uranium enrichment research and to problems of radiation detection. Like many scientists of the era, she found herself pulled into a war-driven urgency that accelerated the development of physics while also casting a long ethical shadow. After the war, she became a professor at Columbia University and built a formidable reputation in beta decay, the process in which a nucleus emits an electron or positron and a neutrino, transforming into a different element. Beta decay was not only a niche phenomenon, it was a central arena where the weak nuclear force, the force responsible for certain kinds of nuclear transformation, revealed its odd character. To appreciate what happened next, we need to step back into the theoretical atmosphere of the time. In the mid-1950s, physicists believed that the laws of nature respected certain symmetries. One such symmetry is parity, often symbolized as P. Parity is the idea that the laws of physics should be the same if you flipped spatial coordinates, if you replace the universe with its mirror image. Imagine watching a process in a mirror. Parity symmetry says the mirror version should obey the same physical laws. Left and right should be interchangeable at the fundamental level. In everyday life, parity seems plausible because most physical laws, like electromagnetism and gravity, do not care about left versus right. If you drop a ball with your left hand or your right hand, gravity behaves the same. A mirror image of a planetary orbit is still an orbit. Parity symmetry had become a deeply trusted principle, but there was a growing unease. Certain particle decays, particularly involving strange particles, seemed inconsistent and confusing. Two decays looked like they involved the same particle, but produced final states with different parity properties. This was called the tau-theta puzzle. It suggested either that particle classification was wrong, or that parity might not be conserved in weak interactions. The idea that parity could fail was shocking. It was like suggesting the universe has an intrinsic handedness. Two theorists, Sung-Dao Lee and Chien-Shiung, examined the foundations of parity conservation and realized something astonishing. Parity had never actually been tested in weak interactions with decisive experiments. It had been assumed because it held elsewhere and because it was aesthetically compelling. Li and Yang proposed that parity might not be conserved in weak interactions and suggested experimental tests to find out. This is where Wu enters as the person capable of turning a radical theoretical suggestion into a factual verdict. Wu understood the experimental difficulty immediately. To test parity conservation and beta decay, you need a situation where left and right matter. You need oriented nuclei, nuclei with spins aligned in a known direction, so that you can see whether emitted electrons prefer one direction relative to that spin. If parity is conserved, the electrons should be emitted symmetrically in a way that respects mirror reversal. If parity is violated, there will be an asymmetry, a preference that cannot be mirrored away. But aligning nuclear spins is not trivial. Thermal motion randomizes orientation. You need extremely low temperatures and strong magnetic fields to polarize the nuclei. You also need a radioactive source whose decay properties are appropriate and whose environment can be controlled. And then you need detectors capable of measuring the angular distribution of emitted electrons with minimal systematic error. Wu chose cobalt-60, an isotope that undergoes beta decay. She collaborated with colleagues at the National Bureau of Standards, including Ernest Ambler, and designed an experiment that required cooling the sample to near absolute zero using liquid helium techniques. At such low temperatures, and under a strong magnetic field, the cobalt nuclei could become significantly aligned. The experiment was conceptually simple. Align the cobalt nuclei so their spins point in a known direction. Then measure whether emitted electrons prefer to come out along that spin direction or opposite it. If parity is conserved, the emission pattern should be symmetric in a mirror sense. Flipping the apparatus should not change the fundamental behavior. If parity is violated, the electrons will show a directional preference tied to the nucleus's spin, a built-in handedness in the weak interaction. The result was unambiguous. Wu and her team observed that more electrons were emitted opposite to the direction of the nuclear spin. The weak interaction, in this decay process, had a preferred handedness. Parity was not conserved. The shock of that cannot be exaggerated. A principle treated almost as an aesthetic law of nature. The universe doesn't care about left or right, was suddenly false, at least for the weak interaction. Nature did care. The mirror universe was not equivalent. There was an asymmetry built into the fundamental laws. What does it mean in a deep sense for parity to be violated? It means that if you build a mirror image version of a weak decay process, it does not occur with the same probability. The weak force distinguishes between left-handed and right-handed configurations. This discovery reshaped particle physics. It forced theorists to rebuild the theory of weak interactions. It helped lead to the VA theory, where the weak interaction couples to left-handed particles and right-handed antiparticles. It became part of the foundation of what would later become the electroweak theory and the Standard Model. Wu's experiment did more than test a theory. It changed the way physics treats its own assumptions. It demonstrated that even the most beautiful principles must be subjected to experiment, and that the universe is not obligated to satisfy human aesthetic preferences. And yet, when the Nobel Prize came in 1957, it went to Li and Yang for the theoretical work on parity non-conservation. Wu was not included. This is one of the defining moments in the history of recognition in modern physics. To be clear, Li and Yang's theoretical insight was brilliant and deserved honor. But without Wu's experimental proof, the hypothesis would have remained speculation. Wu delivered the decisive evidence. In many scientific cultures, the discovery would have been understood as shared, theory and experiment together. Instead, Wu's omission from the Nobel became a symbol of a broader pattern: the undervaluation of experimental work and the undervaluation of women's contributions, especially when the narrative of genius is being written by institutions predisposed to see certain faces as theory makers and others as assistants. Wu's colleagues knew her stature. Physicists referred to her as the First Lady of Physics, a phrase that sounds flattering until you realize how often it is a way of placing someone in a category rather than acknowledging them as simply one of the best. She received many honors, including the Wolf Prize and the National Medal of Science, and she remained a towering figure in experimental physics. But the noble omission remains a reminder that science is conducted by humans, and humans distribute recognition with their own biases and blind spots. Wu herself was not known for bitterness as a defining trait. She was known for seriousness, for demanding standards, for a kind of sharp clarity about what experimental evidence means. She also spoke publicly about the status of women in science and education, asking why societies that claim to value merit still waste half their talent by discouraging girls and women from pursuing scientific careers. Her life, like Meitner's, demonstrates that the scientific revolution is not only a story of equations and apparatus. It is a story of institutions, doors, and the quiet violence of being treated as peripheral. Wu's story also demonstrates the power of refusal, refusing to accept assumptions, refusing to accept sloppy measurements, refusing to accept that theory alone can settle what only experiment can decide. In a way, parity violation is the perfect scientific metaphor for the social asymmetry Wu confronted. Physics discovered that nature has handedness in one realm, and the scientific community demonstrated, in its distribution of credit, that it too had a kind of handedness, preferences not rooted in truth, but in culture. The symmetry failed in both places, though for very different reasons. But we should not reduce Wu to a victim narrative. That would be another form of erasure. Wu was a master of her craft, a scientist whose experiments shaped the foundations of particle physics. She did not merely confirm a prediction. She helped force a new theory into existence. She did not merely participate in a discovery. She delivered the evidence that shattered a principle the community had treated as nearly inviolable. If you want a scene to carry her legacy, picture a laboratory chilled to near absolute zero, a cobalt sample aligned under a magnetic field, detectors counting electrons, and Wu, steady, patient, watching for asymmetry. The data emerges. The pattern is clear. The universe is not mirror-symmetric in this domain. In that moment, symmetry is not a belief. It is a tested claim, and it fails. The room does not explode with drama. The drama is in what the result means. The laws of nature have a preference. Reality has a handedness. You have been listening to Scientific Giants who changed our understanding of the world we live in. Today we followed Chien-Shiung Wu as she designed and executed one of the most important experiments of the 20th century, proving that parity symmetry is violated in the weak interaction, and reminding physics that beauty must submit to evidence. In our next episode, we will meet Dmitry Mendeleev, the man who dreamed the periodic table and made bold predictions about missing elements, predictions that turned out, one by one, to be real. Until then, thank you for your attention and your time. This episode was written as a continuous story for the ear. If it moved you, bring a friend along next time. Until our next hour together, remember that the deepest truths sometimes arrive not as a new principle, but as the failure of an old one, and that it takes a particular kind of courage to trust what the data is telling you when the entire community expects symmetry to survive.